I received an interesting question from one of the viewers, and he asked that if Grubler's criteria seem to suggest that odd number of links in a mechanism will not make it move. So 5 bars or 7 bars or 9 bars seem to be impossible. Then how come this mechanism with 5 links moves at all? He had sent a link to this mechanism in a physical form in operation. This is designed by Clemens Torggler, and I highly recommend you see the original one moving by clicking here. But here we'll be only analyzing its degree of freedom by applying Grubler's criteria. The answer to his question is Grubler's criteria is not restricted to two-dimensional mechanisms. It can operate in 3-dimension as well. And in that case, yes, indeed 5, 7 and 9 bars are possible. So this mechanism is very much possible, as you can see in this animation over here. Let us put it in loop and rotate this mechanism so you can have a good look here. So it starts as a flat door, and when it closes again it is flat. So this is this sort of transits into a 3-dimensional space and comes back to its 2-dimensional form. Now let us analyze its degree of freedom. How many links we have, how many degrees of freedom each link brings, and what kind of kinematic pairs we have, and so on. So we will start by counting the links. So here we have the fixed link, that is the wall on which the door is mounted. Then we have these 4 triangular panes, 2 green ones and 2 red ones. So 4 more links. So in all we have 5 links. Now let us count the kinematic pairs. Of course we have the 2 fixed hinges over here and here, and we have 2 movable hinges. They are kind of subtle. They are the fold lines over here, so the diagonals of these squares, if you will. Okay, so these hinges sit between the green and red pins. So there are 2 of them, and finally we have a kind of globular pair or a ball joint over here. Now let us take stock of the degrees of freedom. As you know, now we are in 3-dimensional space. So every rigid body is going to have 6 degrees of freedom. Of course, not the fixed link. So fixed link will have only 0 degrees of freedom. But these 4 links, the 3 triangular panes, each is going to have 6 degrees of freedom. So 4 multiplied by 6, we have 24 degrees of freedom coming in. But we are going to restrict these degrees of freedom. We are going to absorb or nullify these degrees of freedom by applying pairs. So first of all, these 2 fixed hinges have only 1 degree of freedom. They can only rotate. So they have absorbed 5 degrees of freedom each. So I will write 2 multiplied by minus 5. So 10 degrees of freedom we have taken away. Then we have these 2 movable hinges. So this diagonal here and this diagonal here, the fold lines, they too will be having only 1 degree of freedom. So they absorb 5 degrees each. So another 10 degrees we have gotten rid of. And finally this globular pair, or also called as a ball joint, this has 3 degrees of freedom. 3 rotations, rotation about x, y and z axis. So it is going to have just 3 degrees of freedom out of 6 possible. So it takes away 3 degrees. So that way we have 3 more degrees going away. And then if we add up, we are going to get 0 plus 24, 24 degrees of freedom coming in, while 10 plus 10 plus 3 minus 23. So 23 degrees going away. So we are left with a single degree of freedom, and we have a well constrained mechanism.